Okay, let's think about particularly when we have finite difference, we have a multiplier of that, right? When we take a derivative of the kth term in the Fourier series, while when we are dealing with the analytical derivative, we are dealing with a term that is ik. So how does ik relate to this? First of all, we realize they are not going to be exactly the same, right? Okay, so that is actually pretty clear. For example, if delta x is equal to 1 and k is equal to 1, let's say, then sine of 1 divided by delta x of 1 is not going to be equal to 1, right? So my finite difference actually has a lower oscillation speed, right? Because this actually gives an oscillation than the analytical derivative. But as we can see that as delta x goes to 0, my sine of k delta x divided by delta x goes to what? Right? Anybody knows how does this go? I mean, you can use Taylor series if you want.
When k is 1, it goes to 1, right?
If k is equal to 1, it goes to 1, exactly. And if you do Taylor series, the derivative is equal to 1 if k is equal to 1, and if the derivative for any k is actually equal to k, right? So the limit as delta x goes to 0 is this, and because we are multiplying by I here, we basically get exactly the analytical answer as delta x goes to 0, which is a great sign that we are recovering the analytical behavior, right? If we take delta x goes to 0. All right. So basically, what we are illustrating is that if we take analytical derivative, we have one behavior, and if we take a numerical derivative, if we use central difference, we get a very similar behavior, right? And remember what this term does, right? When we plug in the first order derivative, let's go back a little bit, into the original ODE, right? We have this term, right? What it gives us is this term, which is a purely oscillation. It doesn't contribute to growth or decay. And again, if we use a central difference, the term still is purely imaginary, although the speed of oscillation is going to be slightly different unless my delta x is very small, right? But like in terms of stability, discretizing using central difference actually doesn't really give me additional stability. It also doesn't destroy my stability. My eigenvalues in this sense, my eigenvalues corresponding to this term is still purely on the imaginary axis. Now let's discuss how that could be different if we use an upwinding or downwinding scheme, right? So if we shift the central difference to either a left or right biased derivative, how much different would that be? And that comes to the crux of what we can get by using the Fourier stability analysis. So if I take uj plus 1 minus uj divided by delta x, what does that give to me? If my uj is represented by, so let's say uj is represented by summation of k, uk hat times e to the j I k delta x, right? Then correspondingly, my u of j plus 1 is equal to summation of the same kind of u hat k times e to the j plus 1 ik delta x divided by delta x. Again, I split the exponent of a sum into the product of exponents, and one of the product is going to be exactly the same as that, right? So let me just write it down, k to the u hat k of e to the j I k delta x of something minus 1, and that something is e to the I k delta x minus 1. That thing divided by delta x. Now let's start to look at this term, which is a little bit different from what we get before, right? It's no longer the a difference between two exponential functions. It's the difference between one exponential function and one. So we can still write e to the I k delta x as a cosine of k delta x plus I times sine of k delta x. And as soon as we write this, we can see that what we get is not going to be exactly imaginary. We have actually introduced the real component, which contributes to either growth or decay, right? Depending on where that real component actually turns out. So that the green one is k u hat e to the j I k delta x, and there is going to be a real component of cosine k delta x minus 1 divided by delta x. That's the real component, and minus a, let's see, and plus a I to the sine k delta x divided by delta x.